Hello, today we're going to talk principally about some of the new tools in LUSAS release version 19. My name is Terry Cakebread and I look after our business in the Americas, and today I'm ably assisted by Andy Taylor, one of our training and support engineers. Please feel free to ask questions by typing them into the chat box here. Any questions we do not have time to answer live will be answered in due course after the webinar. So firstly, let's look at steel composite bridge decks, which present some particular challenges in terms of analysis and design. Traditionally, these have been modeled as grid or grillage models, but studies have identified some weaknesses in the grid grillage analysis approach, particularly for bridges which are curved on plan or heavily skewed. The NCHRP report 725 identifies inaccuracies up to 30% for grillages, even just in the major axis bending stresses, depending on curvature, skew, continuity, and cross-frame arrangements. LUSAS version 19 includes a range of new or improved functions which have composite bridge decks in mind. For rapid model building, here I'm referring to both our new wizard for creating 3D beam and shell models and our new tools for grid or grillage models. Our influence surface facilities, which work with the vehicle load optimizer. Branched analysis to give more flexibility when modeling staged construction sequences, and deck temperature profiles, and design checking to AASHTO for the United States, adding to our existing Eurocode facilities. Here's a plan view of a typical curved girder bridge. 3 spans, curved on plan, interior supports skewed. 4 girders, various bracing arrangements used across the spans, and fundamentally the engineer can choose to idealize that structure using a grid or grillage model or using a 3D shell and beam element model like this. If they want to do this kind of model, that's typically quite a tricky job. So version 19 introduces a parametric approach where you define the bridge, the plan curvature, number of spans and support definitions, supports, the skew, the restraints, the bracing arrangements, of course the sections and the materials, where each section is applied, the stiffeners and intermediate bracing, and then essentially you click create model and you get all the points, lines and surfaces, mesh attributes, thicknesses, cross sections, materials, supports, all that is done for you. More importantly, the model can be changed and edited as well within the wizard or at a later stage. And if you deactivate the deck, you can see the results for the dead load on the bare girders, and the improved slicing tools, as we see here, give you non-composite moments, shears, etc. And of course, similar results are available for the fully composite bridge as well. What's also new is that we can now create influences on slice effects. So this is the influence surface to create traffic loading based on the bending moment in the composite girder at midspan of girder 2. It's not the tension in the top flange or compression in the bottom flange. It's the actual overall bending for that girder, which is made up of shell elements and beam elements. Essentially, this means that your more elaborate shell and beam model can give you output just like a grillage, and even traffic load patterns just like a grillage. Moving into the new design checking functions, we set up some basic AASHTO options. Here choosing not to use the simplified checks of Appendix A6, instead full checks for horizontally curved girders and entering the ADTT for fatigue checks. We go on to identify construction and in-surface load cases or combinations, and a member dialog allows full information to be selected, such as steel grades, detail of shear connectors, and locations for checks, and so on. Summary results become available, so we can view, for example, strength checks, where we can see the utilization ratios for flexure and shear in the two rightmost columns, or the bearing stiffener checks, and here we can see any problems highlighted with red text. With a right click on the row, we're able to see a short form summary of the calculation or a more elaborate blow-by-blow calculation showing all the equations with numbers substituted at each step with each article referenced. Note these calculations can be printed or added to the reporting part of LUSAS, in which case if the model is changed, they will be automatically updated in the report. You also get stress plots built up over the construction sequence, this one over an internal support where the reinforcement is in tension. The scope of the designer is currently I sections in flexure, which is Article 6.10. The checks include constructability requirements in Article 6.10.3, service limit state to Article 6.10.4, fatigue and fracture for shear connectors and webs to Article 6.10.5, flexural effects for composite and non-composite sections to 6.10.7 and 8, or optionally Appendix A6, and shear connectors and stiffeners. So now let's have Andy show us a quick run through the Composite Bridge Design Wizard.
Thank you, Terry. So the Composite Bridge Wizard is aimed at steel concrete composite structures where the slab and girder webs will be modelled as shell elements, with the girder flanges, stiffeners and bracing modelled as beam elements. There are quite a few inputs required for the wizard. First of all, you need to define your cross sections, so your girder and your slab. You then need to define a girder, which specifies how the cross sections run into each other longitudinally in order to define a single girder. You then need to define a span, which is basically which girders are adjacent to each other. You also need to define your supports, you need to define any stiffeners, and finally bracing. And lastly, you need to define your overall bridge layout. So in this example model, I've gone for a curved structure on plan with a radius of 600 feet. You can then generate the geometry for the model through Bridge, Steel Composite Bridge Wizard, Generate Defined Bridge. Now it does take a couple of minutes, so here's one which I've completed earlier. So as we can see here from the geometry on this plan view, we can see the curve that's been put in following the 600 feet radius. And if we rotate the model and zoom in a bit, we can see the cross bracing, etc. If we turn on fleshing in order to see the rendered dimensions of all of the elements within the structure, we can see the deck slab, and if we rotate the view from underneath, we can see all the cross bracing and the longitudinal flanges on the beams as well. Now in this completed model, I've already defined the stage construction and the live load cases, and what I'm going to do now is I'm going to carry out design checks for girder 2. So girder 2 is all of these elements you can see here highlighted in black. And what we're going to do for the design is we're going to consider all of these highlighted elements acting compositely together as one single beam. In the Utilities tab, we've defined this girder 2 composite member. Within here, this specifies various information that's been taken from the wizard that created the model, such as the span lengths. But we've also input the shear connectors for the shear design, and we've also specified the design locations. So what positions along the structure do we want LUSAS to carry out the calculations? And they're shown here dotted in red, and you can add additional ones if you want to. We've also defined this composite girder design results, which specifies, for example, which load cases are used for what. So if we look here in strength, we've specified that load case 104 is the dead load case. Load case 100 is the strength factored of dead load plus wearing course. And load case 46 is the live load cases suitable for design of girder number 2. If we then right click and show results, LUSAS will show us a table of the summary of all of our calculations, and we can see here that, for example, for this check, the utilization is 0.91. If we right-click in Detailed Calculations, we can get LUSAS to give us fully rendered calculations, which would be suitable for printing out and putting in our project folder. So we can see here, if we go into this particular design check, we can see all of the design calculations that have been carried out, along with clause references, and we can see the final part here. The utilization is 0.915 by comparing the required pitch to the actual pitch. And we can print out these calculations if we want to put them in a project folder, or add them to a report within LUSAS in order to output them with the rest of our results from our LUSAS model at a later time. Back to you, Terry.
Thanks, Andy. I just want to now go back and show what the vehicle load optimizer does with those influence surfaces with reference to standard AASHTO on the curved bridge which we've just been showing you. The curb lines are defined by the user, and then the vehicle load optimizer, if working to standard AASHTO, divides the space into 12-foot lanes. So these two black blobs are the actual curb lines, as you can see here and here. And this red bit is the remaining area, which is about 1'6" in this particular case. And then this remaining area will then be positioned automatically such that the loaded lanes are in the most onerous location. The vehicles will then run up and down the lanes in and out of the plane of the screen that we can see here. And the notional vehicles, which are 6 foot wide, and the lane loads, which are 10 foot wide, are positioned transversely within each lane to give the most onerous effects, bearing in mind the rules about proximity to the edge of a lane, curb, or railing. The variable axle spacing in design trucks will take the most onerous value between 14 foot and 30 foot for each truck, and any relieving axles are omitted. So for moments over internal supports, often two vehicles are used with a 90% factor. This optimizer has the standard rules and the majority of the state implementations, and works to the Canadian code and many other international codes as well. With the vehicle load optimizer finding the most onerous effects for girder 4, for example, using these curb lines and the HL93 loading from AASHTO LRFD, we see that here we have only 2 lanes loaded, so the multiple presence factors are considered, and the sagging at this location is maximized by using 2 lanes with a higher factor rather than 3 with a lower factor. The other important point to notice is the influence surfaces can be viewed and the load patterns, so the engineer can check the validity of the loading. Alongside our vehicle load optimizer, you'll also find our railway load optimizer, which works to many codes, including United States and ARIMA Chapter 8 for concrete bridges and Chapter 15 for steel structures. The alternative to the 3D model, with a slicing of course, is to actually use a grillage model. And we know that for certain situations, many bridge engineers do favour that simplified approach. So we've added to the grillage tool, which Andy will show you in a minute. These parts come together with our analysis tree again, so you assign the section shapes once only in the base analysis, along with the short-term material properties, say, because the long-term material properties might be assigned in analysis 2, and the wet concrete in analysis 3. The calculations to Hambly or the NCHRP report are handled from there. Furthermore, we've added the ability to insert branches from any stage in any construction sequence. That could be one or more linear static load cases in one or more stages, perhaps to consider some plant or construction equipment moving around the site, or it could be an elastic analysis or elastic buckling analysis for this stage of construction, or indeed full non-linear buckling analysis for this half-completed structure, or an alternative construction sequence, a natural frequency analysis, or even a transient dynamic analysis such as a seismic event. Indeed, any analysis type can be a branch. And if you change the branch, LUSAS doesn't need to rerun the main trunk analysis, so it's really time efficient as a facility too. So now Andy will show us a brief run through of the Grillage Wizard.
Thank you, Terry. So the new grillage section definition under attributes geometric bridge deck grillage allows you to define for the longitudinal section your girder, your slab. Your slab could have an effective width if you wanted, or your slab could be tapering, or you could even have a tapering effective width if appropriate. You also define how your girder and slab interact. So is the slab considered uncracked or cracked in tension? And you can control how the torsional constant is worked out as well. For the transverse members, under attributes geometric bridge deck grillage for slab, you can also have cracked or uncracked sections. And if you had a voided slab deck rather than a beam and slab deck, there are also voided options. You can also define material properties suitable for grillages through attributes material bridge deck grillage, such as this one I've previously defined for dead load, where for the slab we've given it mass but no stiffness. This is appropriate when the weight of the wet concrete from the slab is being supported by the girder alone rather than the girder and slab combined section. I've also got this long-term property where both the slab and the girder have stiffness, but we're not looking at mass. We're not using this for the dead load. This would be suitable for surfacing load or other long-term superimposed dead loads. Within the Analyses tab, I've assigned these different materials in different analyses. So Analysis 3 for the dead load has the material for dead load and also any load cases appropriate. If we now switch to looking at the stresses, we can see here in the dead load case that we've got stresses on the beam section alone, whereas if we look at Analysis 2 in our surfacing load case, we can see the stresses caused by the surfacing load on the beam and slab combined section. Back to you, Terry.
Thanks, Andy. Furthermore, we've also added codified bridge deck temperature profiles to AASHTO, Australia, and the Eurocode, with a choice of approaches, a choice of national annexes, and deck type. And then with a few more inputs, we're able to create two attributes, one for the deck warmer than the girder, and one the other way round. These can be used with a grillage type model to apply the appropriate overall moments. If your code isn't covered, or if you have some special temperature profile to consider, don't worry, because you can enter your own profile, either just entering depths and temperature values, as in this example, or as in this example, using a formula to handle sections of different depths or tapering sections with just one definition. So LUSAS now covers from analysis to design code checks. Tools are available for reinforced concrete beams and columns, slabs and walls, steel frame members, steel concrete composite bridge decks, as we've just shown, track structure interaction, and even train structure dynamic interaction checks. The RC Frame Designer offers ultimate limit state and serviceability limit state checks, including crack widths for biaxial bending, together with overall tension or compression for reinforced concrete beams or columns or piles. In fact, any shape of cross section and any reinforcement arrangement. And you can view utilization contours, as we can see here. You can also examine the calculations for any location and even view moment and axial force interaction plots and interaction diagrams in 2D and 3D. The reporting is transparent and comprehensive, and this RC Frame Designer produces detailed reports and checks to many codes, including AASHTO, Canadian Code CSA S614, and Eurocodes. To upgrade to use the new RC Design module, you can simply complete the form on our website, and as a special offer, this is 50% off for orders placed before the end of September. The RC slab and wall designer, which is included with LUSAS, offers checks for plate bending, including twisting for ultimate limit state using either the wood armor approach or to incorporate in-plane tension or compression using the Clark-Nielsen method. Output can include contours of utilization, or in this case, for the required areas of steel, for example, and it carries out serviceability checks, including crack widths based on principal moments and stresses. It covers the same Eurocode parts and national annexes as the RC frame designer, and also some now withdrawn British and Singaporean standards, plus various bridge and building codes listed here for the US, Canada, Australia, India, and even the Chinese bridge code. Cousin to the RC frame designer, the optional steelwork designer carries out checks on beams or columns or truss members and offers both contours of utilization for the critical check like this one, or indeed each check in turn, and detailed, transparent, claused referenced calculation. Again, these calculations can be printed or added to the reporting part of LUSAS, in which case, if the model is changed in any way, they will automatically be updated in the report. The Eurocode building and bridge codes are covered along with US, AASHTO, plus in version 19, the AISC 360 and Canadian codes, and Australian and Chinese code. And as we have seen, there's a focus in version 19 on steel and concrete composite bridge decks, including faster and better modeling, along with optional design checks to the AASHTO code alongside our existing Eurocode product. LUSAS also has a range of tools for post-tension structures, including the calculation of tendon losses and creep and shrinkage in beam elements, shell elements as seen here, and solid elements. These haven't changed in version 19, so they're not part of this general presentation, but you can find out more on our website. Our rail track analysis facilities enable a fast assessment of track structure interaction according to the Eurocode and UIC 7743, with wizards to automatically create models that have all the necessary nonlinear functionality, and wizards to obtain all the forces, displacements, and accelerations rapidly and conveniently. Improvements in version 19 here now allow the location of bearings inboard of the deck ends, leading to a more accurate representation of the deck and rail system, and also allow the definition of multiple train loading groups, making the consideration of many train configurations much more efficient. For train structure interaction, there is what we call IMD Plus, which has been used in North America, UK, and around the world. Here's an example steel bowstring arch railway bridge designed for the new generation of 140 miles per hour trains. It carries the two tracks of the East Coast Main Line. LUSAS was used to carry out detailed dynamic interaction analysis for rail track, and the interactive modal dynamics techniques used greatly reduced the time required to assess the dynamic response of the structure for numerous combinations of different moving train loads and speeds. This tool will move many different train configurations represented as true sprung masses across structures at variable speeds to help identify the critical speed for dynamic interaction between the train and the structure. Here we're looking at accelerations, and we can see at around 57 miles per hour, or 85 miles per hour is where we're getting the maximum vertical acceleration. From the model, one can obtain, for example, forces in the track components, girder stresses, displacements, velocities, accelerations, and whilst this is valid for linear response, it's also extremely useful in finding out critical speeds and train configurations for non-linear structures as well. Moving on, many of our clients already use LUSAS for analysis on their retaining wall or the dam, wind farm, or even tunneling projects. Applications like these typically require a more comprehensive model of the soil or geotechnical conditions than some other projects might need. LUSAS has a range of tools which our clients utilize, from springs to trilinear joints through to continuum modeling with nonlinear soil materials and contact joints, slide lines, soil interfaces, and indeed full staged construction facilities. And LUSAS 19 includes some new facilities which have been developed with these soil applications in mind. The Phi-c reduction method gives a safety factor based on the soil strength reduction analysis, which indicates how the available soil strength compares to the soil strength required for equilibrium for a given set of loads. So it's typically used for slope stability or retaining structures. Whatever the situation, it's always as simple as defining and assigning a Phi-c reduction attribute, and when you solve, the soil strength will be incremented downward until failure in order to determine that safety factor. So Andy will now show us the new geotechnical Phi-c analysis tool.
Thanks, Terry. So this 2D analysis model considers the slope of a cutting excavated in stages. We can define soil materials in LUSAS through attributes material geotechnical, where in version 19 we've added the Hoek Brown material model, but in this particular model I've used a more Coulomb material. Within that material I've used the K0 initialization in order to specify the at-rest earth pressure, which will allow us to start with the correct at-rest soil stresses. I've also defined which parts of the model are going to have this Phi-c material strength reduction using a Phi-c attribute. In this example, the Phi-c reduction attribute has been applied to the whole of the model, but in a model with more than one retaining wall or more than one slope, or possibly of several different soil materials, you can use multiple different Phi-c attributes and assign them to different parts of the model. The nonlinear controls in this model include displacement reset in the first load case, and this allows us to ignore any deflections which occur under the self-weight of soil while we're setting up the initial state. In version 19, we can add branches throughout any point of the stage construction, and this branch could allow us to do a Phi-c slope stability analysis. In this particular model, I've only put in one slope stability check, and that's right at the end of the construction stages after layer 5 has been excavated. If we look at the results, what we can see is a classic slip circle failure and a safety factor of 2.253. The same approach can be used for both slope stability and for retaining wall structures, and as well as doing it in 2D, in LUSAS we can also do this in a full 3-dimensional model. Back to you, Terry.
Thanks, Andy. So, just another thing I think we should mention is reporting from models, because it's very important, and the built-in report writer compiles graphical results, plots, graphs, results tables, design calculations, and even just model data automatically and in a repeatable way from views and slices of your model. So that way they're always up to date with any changes that you make to the model. You can even have multiple reports and reports in many differing sets of units. And whenever you click, it generates live and up to date. You can easily generate tables of data by referencing in your print result wizard tables, and you can also add your own notes to the model and reference them in your reports too. In this new release, there are 6 new and updated examples in the online manual to help you go through the new tools that are in this new version of LUSAS. Of course, the online help also has details of what is new in version 19 generally, some of which we've not had time to cover today. So just to refresh, to upgrade to use the new design modules, or indeed the RC design module, which is 50% off this month, simply complete the upgrade form on our website, or you can send me an email. So in conclusion, the new facilities for steel composite decks mean that LUSAS now offers a real end-to-end analysis and design solution for both the US, Canada, and Eurocode regions. From wizards to help you build your model, 3D or grillage, through loading, construction sequences, and all those other considerations, right onto the clause checks and the transparent calculations you need for your files. This is complemented with improvements for slope and retaining wall stability analysis. More productivity, more design, LUSAS version 19.